3.2 measurements. Questions. Why can't I measure something exactly? Why do I need to be accurate and precise? What affects the precision of measurements? What are significant figures? Terms accuracy, precision, significant figure. Is being accurate and precise the same thing? The limitations of measurements. The Greek philosopher Protagoras once stated that man is the measure of all things. According to that statement, man is the determiner of all reality. He determines right and wrong and good and evil rather than God. If humans were correct in every life decision and absolutely accurate when it comes to things like measurement, there might be some reason to trust human abilities. But people aren't able to measure anything with complete accuracy. Since the fall, our abilities have been permanently affected. Scientists recognize that there is always some uncertainty involved with any measurement. There is always a difference between our measured values and the actual values of those measurements. While we should always strive to measure as exactly as possible, it is impossible to measure the true value of any dimension. Scientists strive to be both as accurate and precise as possible. Accuracy. The accuracy of a measurement or instrument is a numerical evaluation of how close a measured value is to the expected or accepted value of the dimension being measured. For example, if the accepted value for the length of your textbook is 27.6 centimeters, and you measured the length as 27.7 centimeters, then you made a fairly accurate measurement. But what would you say if you measured it later with a different ruler and your measurement was 27.9 centimeters? Since the accepted length is 27.6 centimeters, there is some uncertainty in each of your measurements and more in the second than the first. Where did this uncertainty come from? The first possibility is that you made a procedural error. You can check for that by repeating your measurement. There is also the possibility that there is uncertainty in the instrument that you are using. When scientists consider the uncertainty in an instrument, they refer to both random uncertainty and systematic uncertainty. Random uncertainty accounts for the slight variations when the same person makes repeated measurements with the same instrument. This uncertainty can cause the measurement to be greater or less than the actual measurement. But systematic uncertainty typically will skew the measurements in only one direction. Sources of systematic uncertainty could be a tape measure that has been stretched or bent, or a balance that reads 0.2 grams too much mass due to improper calibration. All sources of uncertainty guarantee that we can never measure exactly. Scientists try to quantify uncertainty in measurements using various statistical techniques. In this course, you will use a relatively simple approach to uncertainty analysis that compares the measurement uncertainty with the size of the measurement, a quantity called percent error. This technique assumes that you know what the measurement should be. The formula for percent error is shown below. Percent error equals open parenthesis value observed minus value accepted close parenthesis divided by value accepted close parenthesis. 100%. This calculation can yield either positive or negative values depending on whether an observed value is too high or too low. In some applications, we are interested in only the magnitude of the percent error. In such cases, you will include absolute value signs around the numerator of the fraction. Written this way, the formula determines the absolute percent error. Absolute percent error equals open vertical bar value, observed minus value accepted, close vertical bar divided by value accepted, times 100%. If the percent error is small, then the measurement is considered to be accurate. Otherwise, it is inaccurate. Large and small is a subjective matter that depends on the specific application and the need for a particular degree of accuracy. Precision. Accuracy and precision are two terms that are often incorrectly used interchangeably. While accuracy indicates how close a measurement is to the actual value, precision is an evaluation of the exactness of a measurement or a measuring instrument. It indicates how repeatable a measurement is, or how exactly one can make a measurement. Precision does not say how correct a measurement is. Certain numbers can be known exactly. For example, you can count the number of beakers on a shelf. Counted numbers are exact. Some dimensions used in science are known exactly because they are defined. The speed of light, the second, and the meter are known exactly because scientists have defined them as a specific value. But measurements do not have unlimited precision. Whenever we use an instrument to make a measurement, we translate the dimension that we measure into a number by using the scale on the instrument. The digits that we record in the measurement depend on how many of the large and small scale markings are known. These are the digits that we are certain about. But all measurements will include an estimated digit. When you use an analog, non-digital metric instrument, you should estimate the measurement to the nearest tenth of the smallest whole decimal subdivision on the instrument's scale. For example, if a ruler is marked to the millimeter, then you should estimate the digit for the tenths of a millimeter place. If you are using a graduated cylinder that has 0.2 milliliters as its smallest marking, you can estimate to the tenths of a milliliter. You are limited to the tenths place because the smallest whole decimal mark is the milliliter. Instruments with finer scale graduations allow us to know more decimal places with certainty, and therefore our measurements are more precise because we know them more exactly. Does making accurate and precise measurements make a difference? Think back to the chapter opener. As costly as that error was, it didn't put any lives at risk. But there have been situations where lives have been endangered due to errors regarding units and unit conversions. In 1983, an Air Canada flight ran out of fuel due to confusion between pounds of fuel and kilograms of fuel. Happily for the 69 people on board, the pilots were able to safely land the plane at a closed Air Force base. Medical errors can put people's lives at risk too. Doctors prescribe medicine according to one's weight. Therefore, a patient's weight must be accurately known to calculate proper dosage. A nurse must then measure the proper dose before giving it to the patient. Errors in either of those measurements could be a matter of life or death. In one case, a patient had been prescribed 0.5 grains of a sedative. Instead, the patient was given 0.5 grams, more than 15 times the appropriate dose. The error was quickly discovered and the patient made a full recovery. We must always strive to be both accurate and precise because lives may depend on it. Integrity in measurements. One purpose of this course is to train you to think like scientists as much as possible, to become student chemists. Scientists are acutely aware of their limitations, especially when it comes to measuring. For this reason, you need to be familiar with the uncertainty associated with measuring data. Scientists try to report their quantitative results in the most accurate manner possible. To do this, they follow a set of rules for determining which digits of their answer are reliable or significant. Minimizing uncertainty in measurement is an important part of experiment design. Estimating the uncertainty of measurements is important when evaluating the validity of conclusions that are made on the basis of measured data. Scientists must also report measurements correctly because it is a matter of integrity. Reporting measurements with more precision than was actually measured is dishonest. Reporting with too little precision is sloppy and calls into question the validity of one's data. Scientists who falsify data lose their colleagues' respect and perhaps even their jobs. Similarly, you must make the correct reporting of measured data a matter of personal honesty in your work and as you imitate Christ in your life. Scientists constantly face the demand to make moral choices. The choices are similar when a scientist is alone in his laboratory. He may be tempted to falsify data on an experiment. However, Christian scientists must honor God in their measurements. A wise king once wrote what he has. God says, "A false balance is an abomination to the Lord, but a just weight is his delight." Proverbs 11:1. Deception through falsifying measurements is clearly displeasing to God. Many Old Testament passages connect righteousness to right weights and measures. And just like physical measurements, all things are measured against a standard, the standard of the Bible. Significant figures. When recording data, read the temperature indicated on the thermometer in the image at left. The major divisions are labelled every 10 degrees Celsius, and the minor unlabelled divisions mark every degree. The fluid column is past the 22 mark, but it doesn't reach 23. You will have to estimate between 22 degrees Celsius and 23 degrees Celsius. Since the thermometer is calibrated to the ones place, we will estimate to the tenths place. It looks like 22.6 degrees Celsius. We always measure to 1/10 of the smallest whole decimal increment. So even if the thermometer were indicating exactly 24 degrees Celsius, you would still record the measurement to the tenths place, 24.0 degrees Celsius. The uncertainty of the tenths digit is why the last digit is called the estimated, uncertain, or least significant figure. It would be improper to report more decimal places for this temperature. You can see from the preceding discussion that in that temperature measurement, only 3 digits were significant. These are what we call the significant figures, SFIs, of that measurement, that is, those that are known for certain +1 estimated digit. We estimated the digit in the tenths place because the ones place was the smallest subdivision on the instrument's scale. Therefore, the rightmost significant figure will always be the estimated digit. The purpose of significant figures is to indicate the precision of your measurement. Doing so protects the integrity of the data. Significant figures in recorded data. When scientists record their data, they record only the significant figures. When you work with another person's data, you must be able to quickly determine which digits in a measurement are significant, especially if you are going to perform calculations with them. Below are some easy-to-use rules that will maintain precision in solutions to chemistry problems. You may ask, what about measurements that end up as whole numbers? For example, consider 2,500 milliliters. The rules don't address a number like this because it is ambiguous. Whoever measured the volume as 2,500 milliliters could have measured to 2, 3, or 4 significant digits, but there is no way for us to know which when the number is written this way. In cases like this, assume that the ending zeros are not significant. But we can eliminate this kind of ambiguity by using scientific notation to correctly express measurements. Look at the 3 examples at right. You should see that using scientific notation eliminates all the confusion about significant figures in these cases. If you think about it, you may realize that significant figures not only tell us about the precision of measurements, but they also tell us about the instruments used to make those measurements. If we look at the measurement 35.47 centimeters, we recognize that there are 4 SFs. The digits 3, 5, and 4 are all certain, and the 7 is uncertain. The measurement was taken precisely to the hundredths place. So what does that tell us about the instrument? For the scientist to estimate the last digit to 1/10 of the smallest marking on the instrument must have been 0.1 centimeter. Let's practice determining the number of significant figures in measurements.